Hi statistics student, this video is for chapter 8.3, confidence interval for population proportion. So we have a sample, and in this sample we are not measuring anything. This sample is a categorical data sample, so we are counting percentage of a category, and we are counting something that we want to count, and we call it success. So does this sound familiar? This sounds familiar when we are doing binomial distribution. Do you still remember? So these are closely, so when we talk about population proportion, it's highly related to binomial distribution. That means you are counting, you have a fixed trials, you have a fixed sample size, and then out of this sample size, you are counting the number of success. You are counting how many of them belongs to a success category. So because when we're doing binomial, we know that the mean of a binomial distribution is NP. N times P. P is the proportion of success in one trial. The standard deviation is square root of NPQ, where Q is 1 minus P. So it turns out that these kind of number of success in a sample of size N is normally distributed. So let me show you by illustrating in a binomial calculator. So this is a binomial calculator where from online stat book. I think I told you before that the restriction is the P is only allowed we only allow 2 decimal places in P. So but it is good at that it tells you the percentage of each X, right? So out of 12 sample size, what is the probability that I have 6 success if the chance of each one is 0.5, right? So you can see that this looks very normally distributed, right? If I increase this to 100, we calculate, you can almost see that it is normally distributed. You may say, Ms. Chen, because your P is 0.5, so it is symmetrical. So what about if it's not? If it's 0.2? Okay, so we calculate. This is still very normally distributed, right? We can say, oh, about 50. Right? No, about below 50. What is the chances below 50? What is the chances about 25? Oh, about 25. Right. How? Yeah, about 50. How come I? Oh, yeah, it's about 50. It's like that. Okay, it's because it's 20. It's the P is 0.2. So if you say below 12, then you can see that it is about like that. So it is the distribution of X is normally distributed. And then after you do a little bit of research, you can see that like what we say here, this only works if N times P and N times Q are most greater than 5. So if the expected number of success is greater than 5, expected number of failure is greater than 5, then they are normally distributed. And with the mean is NP, the square root, the standard deviation is square root of NPQ. Okay, so because of that, then if I want to do the distribution of P hat, so this is the distribution of X, right? The distribution of P hat will be divide everything by a fixed number N. Then all of a sudden we have the mean is X over N, and the standard deviation of square root of PQ over N. So it would be as if we are doing X bar, except now we are doing a distribution of P hat, where P hat is X over N, number of success over the sample size, and it is normally distributed with a standard deviation of square root of PQ over N. So because P and Q are both unknown, so we would approximate it by P hat Q hat over N. What is P hat Q hat? P hat is X over N in the sample, and Q hat is 1 minus P hat. So it's the number of success percentage, and it's the number of failure percentage in the sample. Okay, So let's look at how we do. So that means if I have a sample and I have a population. Okay, so go back to this. So we have a population. What does estimating population means? That means I have a population of stuff here. They could have different categories. So I don't know. There is a particular category that I count as success X out of the total sample size. Is n. Then I say, well, the percentage of success is called p hat. It's x over n because it's from a sample. But in the whole population, if it is for population, if I count the whole population, I know that I want to estimate the real p. So this is the p that I don't know, the proportion of the success in all of them, the percentage of, maybe the percentage of female, maybe the percentage of red marbles, maybe percentage of people that, want to take the vaccine. Right now it's very popular about if the vaccine is available, are you going to take it, right? So it is a percentage, or now that it's also voting season, we also want to estimate what is the percentage of people that would vote for a particular candidate, right? So it's percentage. To do percentage, you count how many that you are counting over the total. So you use this sample x over n to estimate this. So this is a point estimate. And just like before, we say this is not very accurate because p hat actually fluctuate. It's a sample. If you get another sample, you have another p hat. And then we figure that p hat is normally distributed when? Because x was normally distributed in a binomial distribution. This is binomial. If this is binomial, then under circumstances when x and also n minus x is greater at least 5, greater than or equal to 5, then these are normally distributed with the mean equal to p, and then the standard deviation is square root of pq over n. Oh, it should be like that. Okay, and because we don't know pq, we just use p hat q hat over n to approximate it. Now notice this is an approximation. Unlike in central limit theorem, the standard deviation is exactly sigma over square root n. In a proportion, this is actually approximation. It's square root of p hat q hat over n is how this thing spread out, but it is always normal. So this is a normal distribution with C. Okay, so to find the margin of error, what we do is very similar to the margin of error for mean is error bound for proportion is z alpha over 2 times square root of p hat q hat over n. And once you calculate the margin of error, then you can say, well, the real proportion would be p hat minus e, p hat plus e. Very similar to what you have for mean. And then the point estimate is x over n. X is the number of success of a binomial distribution. Okay, so it is really similar to what we do for population mean, but in this case we are estimating a proportion. For example, estimating what proportion is female, estimating what how many people would vote for a particular candidate, etc., etc. So how do I calculate this lower limit and upper limit? It's very similar to what we have with 8.1. We use this, and we would use, I think you might have seen this before. You use analysis, confidence interval, but you would say proportion one sample. All you need to give is the confidence level, sample size, and the number of success. They actually will calculate p hat for you. Okay, so it's very clean because you are counting the number of number of x that belongs to a category. You just need to give the number of success. Okay. So these are all the explanation, and I go over this. It is really because of it's a binomial, and also NP is X, right? So there's a relationship between P hat is X over N. So X is N times P hat also. So you need to also know this. Okay. So if your expected success and failure is greater than 5, the success or failure is greater than 5, they are normally distributed. And also we also can do the interpretation. So if we have constructed a confidence interval, we would write that, oh, we are 95% confidence in the interval from what to what would actually contain the true value of the population proportion. So this is how you write the interpretation. And we also can say make conclusion. It's the same as what we did for mean. If a particular value is greater than the whole interval is greater than a, then we can say that the proportion is greater than a. If the whole interval is less than a, then we say the actual proportion is less than a. So similar. So let's do an example. A research is conducted to determine how many households use Netflix to stream videos. So that means you want to find the percentage of people that stream videos using Netflix. I think they have a very large market shares, but they want to determine if their market shares has changed or something. So they do a random sample of 500 households, and it shows that 442 households use Netflix. So what percentage is that? So this is a sample, right? So we want to do a confidence interval to compute a confidence interval estimate of the true proportion of households that use Netflix. Now, actually, I think we should say the research is not to determine how many households. It should be the percentage of household, right? We want to see what percentage is using Netflix. So some percent is still using cable, maybe some percent is using other streaming a vendor. Okay, so we would want it. So this is a confidence interval for proportion, right? So it is very easy to find all the information. All we need to know is confidence level and the sample size, and also X. X is what you're counting. You want to do percentage of you people that use Netflix. So 442 is the one that is you're counting. So that's X, 442. So let's input it. Put it in stat this confidence proportion one sample. So 95%, is it 95? Yeah, oh, 90%, 0.9. And they have a sample size of 500. And how many shows up? 442. So a lot of people watch Netflix. Evaluate. So I don't know what the real percentage, the p-hat percentage is actually what? 442 divided by 500 is actually 88.4%, but the error is 2.35%. So that makes it, the lower limit is 0.86%, upper limit is 90%. So it could be in our p-hat is 88.4%, so we can say p-hat is 88.4% because it's 0.884. But the real proportion of the whole population could be as low as 86 and as high as 90 because the margin of error is 2.3%. So find the critical value. Critical value is depending on our confidence level, right? Our confidence level is 90%. So that means the middle is 90. The two side is totally 1%, so one side is 5%, so we'll say z.05. So use normal calculator. So we don't use T calculator, we use normal, inverse normal. Inverse normal calculator. And we put 0.05, and then we calculate. It's 1.645. So 1.645. Okay, so we'll continue in the next video.